In this video, we're going to talk about how to calculate the mean free path of a gas molecule. So what is the definition of the mean free path? The mean free path, represented by the symbol lambda, is the average distance that a gas molecule travels between collisions. So we're dealing with neon in our example. So how far will neon travel before it collides with another neon gas molecule? That's the mean free path. And that's what we need to calculate in this problem. So what is the formula that can help us to get it? The mean free path is equal to Boltzmann's constant multiplied by the temperature divided by 4 pi times the square root of 2 times r squared times p. So p is the pressure and r is the radius of the atom. So we're given the atomic radius of neon. It's 70 picometers. Now the value of Boltzmann's constant is 1.38 times 10 to the negative 23. If you ever forget this number, you can calculate it by taking r and dividing it by Na. So Boltzmann's constant is 8.3145 divided by Avogadro's number, 6 times 10 to the 23. And that will give you that result. Now we want to calculate the mean free path at SDP, standard temperature and pressure. So what is the temperature at SDP? At SDP, the temperature is 0 Celsius, which is the same as 273 Kelvin. And then we're going to divide it by 4 pi times the square root of 2. And the atomic radius is 70 picometers. 1 picometer is 1 times 10 raised to the negative 12 meters. So this is going to be 70 times 10 to the negative 12 meters. And don't forget to square it. Now the pressure at STP is 1 atm. However, the units that we need has to be in pascals, which is newtons per square meter. So 1 atm is 101,300 pascals. So now go ahead and plug in everything and get the answer for part A. So the mean free path is 4.271 times 10 to the minus 7 meters. So that's the answer for the first part of the problem. Now let's move on to the second part. Let me just get rid of some stuff first. Now part B. What is the root mean square velocity of neon? So I'm going to use this formula to get it. It's going to be 3 RT divided by the molar mass in kilograms per mole. So R is 8.3145. It's not 0.08206 for this formula. And we know the temperature at SDP is 273 Kelvin. Now we need to go to the periodic table to look up the atomic mass of neon. If you go to it, you're going to see it's about 20. I think it's 20.18, but let me double check it. So it's 20.18 grams per mole, or atomic mass units. Now, we need to take that value and convert grams to moles. 1 kilogram is equal to 1,000 grams. So if we take 20.18 and divide it by 1,000, it's going to be 0.02018 kilograms per mole. So that's what we got to plug in to that formula. So let's see what this is going to be. So the root mean square velocity of neon is 581 meters per second. So that's the answer to part B. Now let's move on to part C. Calculate the mean free time of neon. So, what equation should we use to do this? Now, since we already have the mean free path, it's going to be relatively simple to calculate the mean free time. The mean free time is simply the mean free path divided by the speed. And we're going to use the root mean square velocity. So it's 4.271 times 10 to the minus 7 meters. And then we're going to divide that by 581 meters per second. And so the mean free time in this example is 7.35 times 10 to the minus 10 seconds. And so that's the answer. Now let's move on to the last part, part D. Calculate the number of neon molecules per cubic meter at STP. So first, let's start with the equation. This is another variant of the mean free path equation. So the mean free path can be described as the volume divided by 4 pi times the square root of 2 times r squared times n. So n is the number of gas molecules in a container of volume V. So our goal is to look for the number of neon molecules per cubic meter. So we need to find the value of n over V. So first, what I'm going to do is multiply both sides by 4 pi square root 2 r squared. So on the left side, I'm going to have lambda 4 pi square root 2 r squared. On the right side, these will cancel. So I simply have v over n. Now I'm going to put this over 1. Now I need n over v, so I'm going to raise both sides to the negative 1. So basically I'm going to flip both fractions. And so 1 over lambda 4 pi square root 2 r squared, that's going to be the number of molecules per cubic meter. So that's n over v. So let's go ahead and use this formula to get that answer. So it's going to be 1 over lambda, which is 4.271 times 10 to the minus 7 multiplied by 4 pi times the square root of 2, and then r, that's 70 times 10 to the minus 12, and then squared. So go ahead and plug that in. So you should get 2.69 times 10 to the 25, and the units are molecules per cubic meter. So that's the answer. Now let's talk about other ways in which we can get that same answer, because this is not the only way. What we could do is convert 1 cubic meter to the number of molecules. So let's start with that. Now it's important to understand that 1 cubic meter is equivalent to 1,000 liters. And at STP, 1 mole of gas has a volume of 22.4 liters. And then we could use Avogadro's number to convert from moles to molecules. So 1 mole is 6.022 times 10 to the 23 molecules. So if you take 1,000 divided by 22.4 and then multiplied by 6.022 times 10 to the 23, this will give you the same answer, 2.69 times 10 to the 25. Now, there's a third way in which you could use the general equation that can help you to calculate the number of molecules per cubic meter given the pressure and the temperature. So let's start with the ideal gas law equation. PV is equal to nRT. Now N, the number of moles, is equal to the number of molecules divided by Avogadro's number, which is molecules per mole. So the molecules cancel, give you N in terms of moles. So let's replace N with the number of molecules per or divided by Avogadro's number. So I'm going to multiply both sides by Na. So on the left I have PV, Na, and on the right, nRT. Now I'm going to divide both sides by VRT. So on the right side, RT will cancel. On the left side, V will cancel. So the number of molecules per cubic meter is going to be the pressure times Avogadro's number divided by RT. Now the pressure is 101,300 pascals. Avogadro's number is 6.022 times 10 to the 23. Now R is 8.3145, and the temperature at STP is 273 Kelvin. So if we plug this in, this gives us the same answer of 2.69 times 10 to the 25 molecules per cubic meter.